Hello, my name is Asia Mary Imitembo, and me and my teammates are going to be talking about interpretable retrieval augmented AI for potato blight disease detection. Plant diseases pose a significant threat to global food security, with blight diseases being among the most destructive for crops like potatoes. These diseases can drastically reduce yields and profitability for farmers. We are going to be focusing on late blight and early blight. Lead blight is a potentially devastating disease of tomatoes and potatoes infecting the leaves, stems, potato tubers, tomato fruit, spreading rapidly in fields, and it can result in total crop failure. It's caused by Umicid phytophthora infestans. Early blight is a fungal disease that affects plants such as tomatoes, potatoes, eggplants, and peppers. Alternaria solani causes early blight, and Alternaria alternata causes the brown spot. Climate change, particularly warmer temperatures, is likely to increase the prevalence of these pathogens. Recent advancements in computer vision and deep learning provide a promising approach for real-time disease detection, enabling farmers to make informed decisions and reduce crop losses. In this study, we leverage the power of computer vision combined with retrieval-augmented generation to develop an advanced system for detecting and managing blight diseases in potatoes. Computer vision is a field of computer science that allows computers to understand and identify objects and people in images and videos. Retrieval augmented generation is an artificial intelligence framework that combines the strength of traditional information retrieval systems, such as databases, with the capabilities of generative large language models. This approach not only facilitates real-time disease detection, but it also delivers personalized data-driven recommendations to farmers, ensuring effective disease management and sustainable agricultural practices. Next, we have the problem statement. The detection and management of plant diseases, particularly late and early blight in potatoes and tomatoes, remains challenging. Current AI systems often operate as black boxes, lacking transparency and trustworthiness, while failing to adapt to diverse environmental conditions. They struggle to integrate multimodal data, such as visual disease detection and text-based insights, leading to generalized, less actionable recommendations. The risks of misinformation from AI-generated content further limit their effectiveness. These challenges demand a solution that is explainable, adaptable, and capable of integrating multimodal data to provide accurate and context-aware disease management. I'll have my teammates walk us through the related works.
Hi everyone, my name is Namakula Josephine. I'm going to start with the literature review. So we reviewed many papers, but one of them, there is detection of potato disease, which is Albright using artificial intelligence. It was published in 2021. The contributions of the authors. There was real-time disease detection, environmental and economic impact, advancing disease identification. The algorithms, there was GoogleNet, VGGNet, EfficientNet. The limitations they faced, there was variable lighting shadow, inference time variability, and class-specific accuracy challenges. The second paper is Albright and late blight disease detection in potato using efficient net B node. It was published in 2024. They developed a highly accurate classification system using efficient net B node, achieving a testing accuracy of 99.0%, surpassing existing methods. The algorithms, they built efficient NetB node. The dataset, which was the limitation, the dataset used for training was relatively small, and also there was an imbalance in the dataset. The third paper was investigating potato late breed psychological differences across potato cultivars with spectroscopy and machine learning. It was published in 2020. The contribution, it is a novel use of in vivo Fourier spectroscopy, genotypic influence on spectral response, application of statistical models. They built random forest discrimination, partially squares discrimination analysis, normalized different spectral index. The limitation, there was limited scope of cultivars and pathogen line. When I go to the next slide, I find the research questions and objectives. The main objective was to develop an AI system combining computer vision and retrieval augmented generation for effective detection and management of late blight and early blight in potatoes and tomatoes. The specific objectives to identify and create data sets suitable for training computer vision models to detect early and late blight, to develop a computer vision model capable of accurately diagnosing blight from crop images, to integrate a retrieval augmented generation system for personalized and context-aware advisory services, to evaluate the effectiveness and usability of the combined computer vision and RAG system for real-world agricultural applications. And these are the research questions this side. When I go to the third slide, I find the systems methodology. The first thing we did was to collect data. It was image data containing late bright, early bright, and the health images. We did exploratory data analysis. We did data selection and processing. We split the data into three parts, which is the test data, validation data, and train. Train data was used for feature selection and hyperparameter tuning. Validation data for model validation. Test data for train model. We trained the model and we developed it. We evaluated the model. We applied explainable AI to the black box models to understand what the models are really saying. We shall also choose the best model. We feed the model in our RAG application, like the results of our model into the RAG application with some text data. So the RAG application will use the data. We'll use the answers from the model and the database to give answers. We will also validate the RAG for user testing, and after we shall do system deployment and continuous monitoring. Thank you for your time. When I move to the next slide, I find a pie chart showing the distribution of the different potato images with percentages, with potato blight and early blight with the same percentage, which is 46.5%, and potato healthy 75%. And this was part of our exploratory data analysis. So the next image is about a bar plot showing that again showing how these images are distributed in our data set into categories of potato healthy and potato late blight with potato early blight. So when I move to the next slide, I find a box plot which is showing the distribution of intensity with our data set. With potato early blight, with no outliers, but potato late blight, it has an outlier here in 150, and also potato healthy with outliers up and down, and the line inside the boxes are the mean values. With the upper line, the upper with the upper class boundary, and the downer one is the lower class boundary. So when I move to the next slide, I find an image showing the original image and the GradCam heat map. The GradCam is the graduate weighted class activation mapping, which is like a heat map showing how different features on the images, how they are related. With these yellow or red regions are showing the areas where the model detected features critical for its predictions. And the red, blue, the rainbow colors here, like here, um, they are showing areas of lower importance for the prediction. Thank you so much.
My name is Osinge Martin William, and I'm going to continue. So when you look at these images here, we have at first the original image, which is just the raw image, which is infected with the disease. And then the second one, we have the image, which the model has, which shows how the model what the model based on to detect the disease. Yeah, and it shows the highlighted areas. So the bright regions, which you can see there, which are colored with colors like red, orange, and yellow and blue. Yeah, those are the regions where the disease is present. And then the cooler colors, the other areas, the regions with less significant, which have less significance, which means they are not really helpful to the model when it is detecting the disease. Yeah, so then in conclusion, while computer vision has proven effective in identifying both late blight and early blight diseases, there remains a need for personalized and up-to-date advice tailored current weather conditions and available data. If I could clarify more on that, yes, computer vision is very effective. However, current systems are not sufficient on their own because uh, the farmers need feedback which is personalized, maybe because different farmers operate in different weather conditions and the available data keeps changing in time. So using up-to-date data and personalized recommendations, which even have more impact on the farmers, would be better. And it is what we are aiming to achieve. Yeah. Then in future, maybe we would like to extend the approach to other crops and diseases. That is, after we have focused on our main case of study here. And then maybe we shall also incorporate larger data sets and refine the model for scalability. Yeah, to use larger data sets would improve the model's performance and it would ensure the system can handle diverse real-world scenarios and maintain high accuracy. If that is done along with maybe expanding the approach, then it would be more helpful, more farmers.